people can come. Yeah. They are more than yeah. Okay. Already. Thank you very much for coming.
Okay, so yeah, so let's start the seminar. So today we have a speaker, Juven Wang. So he's going to tell us about ultra unification, topological order as dark matter. Please start.
Yeah, thanks very much. It's my great pleasure to be here. Let me start my project. Dziękuję za organizację i udział w moim seminarium. Dla mnie wielka radość móc zastąpić swoja prac na Uniwersytecie Warszawskim. Thank you very much for giving me an opportunity to speak here. I really enjoy this Polish culture, and actually one thing I'm coming to Poland is because there's right now this compound competition, the preliminary round, and I really enjoy the music. Attend this event. Yeah, and just please interrupt me and ask questions anytime. So I recently just moved to London, so pretty close to mainland Europe, so I should be able to stop by places like Warsaw near future. And previously, I did my undergrad at in Taiwan, and moved to MIT for my PhD, and I studied at the Institute for Advanced Study. I did my postdoc in Institute for Advanced Study in Princeton, and I worked for a few years at Harvard. Now I'm at the London Institute for Mathematical Sciences. It's a research institute at Royal Institution, which is where Michael Faraday worked before. Okay, so this work is pretty like a new kind of ideas. Try to go beyond standard model and try to connect to physics related to neutrinos and possible in neutrinos. My connection to, in my opinion, connection to topological phase model, topological order of dark matter. Right. So. Okay, let me begin with more like colloquial statement. So we know there are both kind of fundamental forces, and they may not be fundamental anyway, but they may not also be full, but they are the known one that you learn from textbook. So these are the EM, electromagnetic, strong and weak nuclear force, and also the gravity. Somehow physicists believe there's some concept of unification, so at energy scale become higher and distance moving is shorter, then we kind of think there's a particle of physics, there's a unified force. And I believe this is one of the reasons many people here want to do physics, because we're going to see the unification manifest. And one thing of that is electromagnetic EM. Maxwell actually attend the talks given by Michael Faraday in this so-called Royal Institution type of a lecture series. And actually it's where I work right now. And Faraday there is showing the EM induction relation between magnetic field change can induce electric field and vice versa. So this basically is a reason where Maxwell tried to add one terms in the known equation of the EM. So this is a very naive and simple addition just due to the fact of EM duality. But this is a consequence to make the equation manifest in a better way in the, for example, like differential forms or Lagrangian formulations. So today's my talk similar. My goal is question about all the paradigm given us the most standard model and examine more carefully and see whether it's possible that I can even introduce new terms. And for the reason, also pretty mathematical about the beyond standard model physics. So my goal, again, let me just repeat it. Just similar to Maxwell, try to introduce a term. He has a reason for EM duality, but mine is different. I want to introduce some new terms to the quantum field theory standard model. And I'm not going to assume much about quantum gravity or string theory. So my assumption is really simple, just by the known physics of standard model and the Lagrangian theory of particle physics. And the punchline is that in the end, actually the new terms we add will not be a particle physics or quantum field theory, but still some kind of quantum field theory. It's a beyond particle physics quantum field theory. Instead of having some particle description of like a fermions or gauge bosons, like that type of quantum field theory, instead, the new type of quantum field theory will add in this topological field theory, TQFT, that describe excitation of some kind of anyon or fractional statistic type of inductions for strings and anyonic strings or anyonic Wilson line or worldsheet. Okay, so any questions so far?
What is anion?
Oh, anyon, good. So I assume people know boson and fermions. So boson and fermions are still particles in the sense they are identical particle you cannot distinguish. When you try to exchange them, then you can compare the wave function before and after this exchange. For boson, the exchange does not give any additional complex space, which the wave function in quantum mechanics alone, but fermions will give minus sign. Anyons is the case that if you exchange anyons, sometimes it can be given rise to abelian complex phase. So these are statistical phase. Some people may just say this will be a baryon phase when you compute in quantum mechanics, right? In some cases, actually, in our case also included, is that the exchange anyons or some kind of fractional excitations may not even give rise to a complex phase, but even a unitary matrix X on the Hilbert space, such that the eigenvector in the Hilbert space might change to a different vector in the Hilbert space. And I'll explain that. So anyon should be regarded as a fractional excitation beyond boson and fermions. And you will explore the complexity, the complexness of the Hilbert space, and also the multi-dimensionalness of Hilbert space near the ground state. Okay, is this okay? So yeah, I haven't even written down the keyword, but this is all introductory. So this new QFT actually would involve some kind of anyons type of degree of freedom. But I also need to like mention the anyons in the past, like Weyl and others. This anyons exists in 2+1 two-dimensional space, one-dimensional time, condensed matter, quantum mechanical system. But in our world, the standard model is 3+1D. So it will not be a particle like anyons, but it will be more complicated type of object. But it is a bit demonstrates some similar statistics like anyons. Yeah. Okay. Yeah. So please, question will be all encouraged anytime. So my proposal actually will be instead of just new, there's no known forces. Actually, there are new force. And what's that? These are anyon statistics. Some object similar to Aharonov bone effect, by the way, I should mention. Similar to Aharonov bone. Such that objects involving quarks and leptons in my theory, when they braid around objects, which we have not found, but I propose I can write down mathematically some kind of hidden matter. Let me assume it could be dark matter. Then this process from one, let's say quarks is created, maybe anti-quark or lepton and anti-lepton. When they braid along, in a sense, their trajectory wind along the space-time, and such this process has a non-trivial linking in the space-time, then you can measure the interference at n, and that interference has a relation to the charge of this quarks and leptons, and some kind of flux of this dark matter. But this is very vague so far because this is just Aharonov bone, and generally it's not even abelian phase. But I'll describe such a process such that certain kind of interference is predicted in my theory. It means that there's a possible new force between quarks and lepton and dark matter, and which is a topological matter. And that's the main point. There's a new fifth force I propose, and that is to anyons in quantum matter. And I haven't given you any reason, so you should not have a believe in me. You should have a zero trust. But at the end of the talk, I want to ask you a question. Do you believe that's a possibility? So keep your doubt in mind so far. Just don't believe me until maybe you see a reason. I hope the claim is clear. Okay. All right, so this is a fifth force. And what exactly is that? In the standard model, actually, the proposal I will show is actually related to baryon and lepton type of discrete symmetry. In the current standard model, we do have a U1 continuous baryon minus lepton symmetry. By saying so, it means that the U1 is a transformation, is a continuous circle transformation. And the conservation law of U1 says there's a like a Nolan theory in the classical level, there's a conserved number. So this will be the number of B and L. Oh, yeah, the number of B and L is conserved. B minus is a symmetry, and there's a conservation law, is a B minus L number. And that number in the quantum mechanics will be quantized. just like a continuous U1 rotational symmetry, Nolan theorem tells you the conservation of angular momentum, but quantum mechanical angular momentum be quantized, right? So the 0 to 2 pi theta, or the U1, says the concerned number, in this case will be some number is integer z. Okay. But in the case of mine, the U1 in myself can preserve just some discrete subgroup, such that it does still contain the fermion parity subgroup. That means the number symmetry acts on fermion by -1, and boson sector will be +1. So this is called the fermion parity. Just acts on fermion by -1, and boson is +1. I'll consider the extension of the Z2 as a Z2 NF that contains Z2 subgroup, which means the clock of U1 is separated by 2n ticks. The Z2 NF subgroup will also have some preserved number of discrete B minus L. So I hope it's clear. And I propose this discrete B minus L actually is a secret topological gauge interaction. Once the discrete B minus L is dynamically gauged, and I'll give you a reason for that, then actually there's a topological discrete gauge force between the quark and lepton with a hidden matter, which is topological matter. And my proposal is that this matter, the blue one, actually is around us. They have only gravitational interaction and topological interaction. And they will also have interaction, this type of non-matter will have interaction with quarks and lepton, but because the Yang-Mills forces are too strong, so the effect on the quark will be difficult to detect. And that's why the new window to detect this force will evolve in lepton that does not have a charges under the Yang-Mills of the standard model SU3, SU2, U1, or the minimum charge. So the possibility for this lepton will be, let's say, the left-hand neutrino, because it does not charge on the SU3 Yang-Mills and U1 EM. It only charges with the SU2 weak. So that's why the neutrino in this sterile naturally become the window to interact with this dark matters with discrete B plus minus L force. And that possibly also explain the interference effect people observe in hollow bone as an analogy for this effect of mu tau type of left-hand neutrino can interact and interference with this hidden matter. So this is a big picture. Any question? Yeah.
How does one gauge discrete symmetries?
That's good. Yeah. So very good. So now we can ask, how do we gauge continuous symmetry? So yeah, first of all, what do we mean by gauge symmetry then? When you have a symmetry, we say global symmetry. It means this is symmetry transformations, right? It means that the states in the Hilbert space might be transformed under the symmetry, and they are not an equivalent state. Otherwise, you become a redundancy. So when we say there's a global symmetry, it means the state may be changed under the symmetry transformation to a different state in the Hilbert space. When we say we want to gauge this global symmetry, we want to impose some constraint such that similarly different state become the same state as a gauge redundancy. So the mathematical way to say this, which passed in the book that Professor Stefan wrote, is that you should sum over the gauge connections and gauge bundle, and then do a path integral. And the summation can be written as maybe just gauge connection dA in the path integral form. And then you need to be careful about all the possible configurations, and you sum over these configurations gauging. So the simpler way to answer your question is that couple the global symmetry charge with some background gauge field in one higher dimension. For example, you want to gauge 0-dimensional particle symmetry, then you couple to 1-dimensional gauge field, such that particle is at the endpoint of a gauge field A. But now promote this A to dynamical field, and mathematically means sum over all the gauge connection bundle. And this will remove some degree of freedom, and this will become gauge redundancy. And then basically you will identify many states, and this will define a new path integral. So the old path integral before you gauging has a dependent, for example, on A, and new path integral after gauging has no dependent on A when A is sum over. So gauging will be this process. So for continuous symmetry, then will be gauging the U1 continuous symmetry of continuous U1 gauge field. Gauging discrete symmetry or gauging the discrete Z2 and, for example, in my case, of some discrete gauge field. And then which means when you sum over this, it's not sum over the gauge connection over U1, but just discrete value. And you can still do this summation.
So it is just identification of the states that would be normally related under this discrete symmetry if it wasn't gauged, right? So normally we would think about these states as different states in the Hilbert space, and now we simply identify those.
Right. Yeah. And then those states might be discretely non-connected. In a continuous case, they maybe have a
Okay, let's think about the discrete case. That's the question of identification vectors in the Hilbert space.
That's right. Yes.
Yeah.
And I think for string series, sometimes they will use the word like OB4 or something, just in case this is familiar for some people here.
Yeah, so I may be wrong in this statement. Anyway, I won't interrupt him.
Okay, that's fine. It's just there's some summation of a gauge field in the old configuration, and there's states on identification. Okay, so now is that in the standard model scale, B and L, actually we do have a B minus L, continuous one B as L, symmetry is continuous. But I want to propose at some energy scale, actually what this really is above the current state of standard model, actually the real symmetry or real discrete gauge structure, which is not really a global symmetry, but gauge structure, gauge symmetry. Maybe it's not symmetry, but just gauge structure is actually discrete. Okay, I want to give you a reason for that, but right now I'll just say that that's all I'm going. Okay, then we can gauge that, and then become a gauge boson, discrete gauge field. And some people might read the paper of Weyl, and Krauss and know there's a discrete gauge theory of that. Maybe some people know Dago-Witten theory. So these are all kind of discrete gauge theory. Some people might hear BF theory. If not, then you can just think about there is no continuous gauge field of U1 with photons. There's no photon degree fitting anymore. Once you consider only the discrete subgroup, what's gauge? The only entitlement will be topological. Okay, so any question? So maybe let me just say one word in case for ZN gauge theory versus U1 gauge theory. How much people know ZN gauge theory? So U1 gauge theory will be Lagrangian of this F wedge F and F is dA and A is U1 connection. So there's a photon degree freedom. So it's like a wave. There's a propagating mode, and you can change the frequency, and you can probe a continuous spectrum. So the spectrum of that energy level will be continuous in some way, which means that you can change the momentum of the photon, and you can probe all the continuous spectrum. It's like a continuous wave. Zn is gapped in the sense spectrum is actually only have a low energy TQFT, and in fact the TQFT does not describe much. Except there's a desert or island of no state in between in the energy spectrum. So here I'm drawing the energy. So there's a desert, and what's below is actually TQFT, and above that gap is actually what we call anions. And familiar example in 2+1D ZN gauge theory will involve charge Q particles and Q in Zn and charge. And then flux, so this is charge and flux. And flux phi d in this case will be 2 pi over n and times on little n belong to discrete Zn class. When you move these particles around the flux, then what you will observe is the statistical phase that you learn from Ahorn in the BMM. Basically, you can measure the phase after this, either the full braiding, go back to the original, or you can consider quark or anti-quark or electron, lepton, and anti-lepton goes to an interference phase. This will be a phase being measured. So the wave function psi will evolve to psi times this phase. So this is a difference between the continuous U1 with photons versus discrete as Ahorn effect. So this will be an effect I predict. Which I give you zero reasons so far. I just said this is where I'm going. There's a quantum lepton intel with this discrete gauge sector of TQFT. So discrete B minus L gauge force or B plus L, B minus L. Yeah. Okay, any question? Okay, let me keep going. So then the picture will be there will be some new unification involving this process with the O1. And the material theory just through the wall. It's actually TQFT type. It's not a Witten type of SUSY supersymmetric TQFT, but it's a Schwarz type. It's also largely done by Witten by this Chen-Simon-Witten theory. Except his theory is usually a 3D Chen-Simon-Witten. Here in the standard model, we consider 4D theory, and it's not quite a Chen-Simon theory in our case. But it does involve in something similar to Chen-Simon, but I'll basically just say just topological field theory of that type. I didn't write, instead I'll just give you a name, but we'll go there. And in fact, the new sector actually can be involving force gap or gapless, including TQLT or CLT. My talk mostly focus on TQLT, and it can also be CLT. Right now, I said these words, I didn't give you a reason, but the punchline is actually that this sector can be added through a very subtle check about common field series, so-called the anomaly cancellation. And I'm going there for the next few slides. The punchline is that due to that, the anomaly, dangerous. The anomaly of standard model is not quite cancelled through the discrete B plus and B minus L symmetry of the standard model is not quite cancelled. So there is a room we can cancel the anomaly by adding a new sector. So that's why we are going to propose a new sector. Okay. Any question? Yeah, so the punchline is so far as there's a fifth force of topological force will be introduced, and dark matter might contain topological matter and coupled to the standard model, so discrete force. And this is there's a mutual interaction between matter and dark matter, so discrete plus L minus L. There's another discrete force involving dark matter. Okay. And I haven't told you much about what the B and L symmetry is, but we are going there. Okay. But let's just imagine what I'm actually trying to really introduce is actually in the path of unification, from the stronger force to the weak one, the gravity. Actually, there could be a new one we might missed, and it will come together. As actually introduced similar to the thing happening in quantum condensed matter is these sectors might evolve, and such that in the proposal, I do not necessarily require thinking about granular by theory. But you can also consider granular theory, like gauge-gravitational as U5, but it's not necessary. As long as looking at the standard structure, actually there's a room you can add topological sector, such that including topological sector, topological field theory, TQLT, and also the topological matter, anion type, beyond the particle, familiar particle, then actually there's a new sector that interact with standard model. So this picture will suggest the high energy field might contain things beyond standard model. That is not 0D particle physics, but something involving excitation of 1 dimension, 2 dimensional higher. Okay, so this is a claim. Okay, so any question about this claim? Because people might,
But in what sense it's unification?
Right.
Because I mean, if you talk about unification, the intuition is obvious.
Right.
What does it mean? It's one gauge coupling constant.
That's right. That's right.
When you talk about unification of the standard model groups, what is the?
That's mean yes. So this is the things that kind of more disappointing in a sense from going back theory point of view. There's a unification gauge coupling, but in this case, I just introduce new things and then make them work together in a sense of new interaction. I don't have a picture that I'm making the gauge force or gauge coupling written as one single theory. But I will comment there's actually an idea to connect this new sector and known sector, view as some kind of a so-called quantum phase transitions between the standard model theory with 15 biofermion and TQLT sector, and the standard model theory was 15 biofermion and the right-hand neutrino, which is 16 biofermion. Then there's some kind of a topological phase transition. There's a quantum critical point such that the new physics here involving some more unified description of some gapless degree of freedom. This requires some condensed matter thinking, but the main point is that the unification will come in at the phase transitions when the theory becomes critical. And the critical theory happens between phase transition. So the short answer to you is that unification is not manifest at the physics of what I'm going to write by any TQLT, but it will happen when we look into the quantum phase transition between the ordinary particle physics 15 biofermion plus right-hand neutrino, in contrast with the 15 biofermion plus with TQLT. So let me just TQLT. Yeah. So yes. Okay. I hope this is okay. So anyway, so there's no gauge coupling unification because actually gauge coupling is a concept for work for Young males. When you go to TQLT, the coupling doesn't even run. There's no running coupling. There's no beta function. So in the TQA side, you don't really know what's the location for gauge couple neuron. Okay, so now I made a claim, but I want to give you a very simple way to say what's the argument I'm giving. So let me look at something very similar, familiar to you is just a chessboard. Can you identify the missing piece here for me? See who is the quickest one. Which piece is missing?
In reality, the queen.
Huh?
The queen.
The queen, yeah, very good. So you see this is king, and you use the right hand as a queen. But if you look at the pattern, it's very symmetric in the sense the rook, the knight, the bishop, and you might guess this king, then this might be another king. If you just look at the pattern, right? So these are 15 pieces plus 1. So in fact, if you draw the biofermion degree of freedom in the standard model, we do have the following. We have this quarks in 3 color, and these are doubly SU2 in the left-hand one. And then this doubly for new E, neutrino and electron, and similar right-hand one is SU2 singlet. So everything draw that as the SU2, the biofermion, which is the biofermion, which is basically rewrite Dirac as Weyl, left-handed and right-handed, right? So what is missing is this one, the right-hand neutrino. We have not found this one yet, but people propose that. And it seems like people are assuming for some reason right-hand neutrino might be the right degree of freedom. In fact, most of the neutrino puzzle involving some kind of right-hand neutrino. For example, right-hand neutrino might get Marana mass and hide in the deep UV. And right-hand neutrino might pair with the left-hand neutrino with Dirac mass. And there's a diagonalization of the Dirac mass and Marana mass matrix to get a seesaw mechanism to push the left-hand neutrino mass to be small. Right? And etc. So here, I want to question that the reason I'm giving now. Right? No. So the right-hand neutrino may not be the only possibility to be aided. Just like in the chess game, this is not the only thing being symmetry as the king. And in mathematically, we need to give a proper reason. The reason actually is that the whole pattern of standard model involving some kind of anomaly cancellations. So this anomaly cancellation does suggest some degree of freedom can be involved. And that anomaly actually involves the baryon lepton symmetry involving mixed with gravitational type of anomaly. And
sorry, what is wrong about the anomaly of a global symmetry? I mean, there is nothing wrong with the global symmetry.
That's right. Very good. Yes, very good. This is a good question. These are certainly the legitimate questions. So the statement of that is that global symmetry anomaly is also people call Tahu anomaly. That anomaly is just a signature of a theory, and it's an invariant on the RG flow. So there's no problem for that. But the statement here I'm secretly using is the statement say if the whole theory we have believe in is embedded into a quantum gravity theory, then people are saying nowadays and have been saying for decades actually is that there shouldn't be any global symmetry in quantum gravity. So any symmetry.
So it's based on black hole arguments.
That's right.
And black hole arguments are not necessarily valid. Because we do not know what's in the center.
Right. Well, yeah. So let me say my conclusion of what I'm going to claim is that if B plus and minus L is really a secret important global symmetry, then the belief is that this global symmetry either need to be broken at some scale or be gauged, just to be consistent with no global symmetry. So this will be a statement I'm going to use. I agree with you that people use black hole to argue no global symmetry, but I'm only taking the consequence. Say, suppose B plus and L, B minus L is really a good global symmetry. If you want to embed a standard model to quantum gravity, then I will either want to break it or gauge it. And you will see, in fact, the previous scenario involving lepton genesis is the B and B minus L is broken because Marana mass or right-hand neutrino were broken. But my scenario actually is different. You don't break B minus L completely down to fermion parity, which means, yeah, I think, yeah, I can add that slide. Yeah, so this one.
So, but are you going to gauge B minus L?
Yes, you will gauge B minus L. That's right. So that's why I go back to our conversation, gauge discrete B minus L. Yeah, very good. So you get it. So the usual lepton genesis involving breakdown U1 B minus L, say down to the Z2 fermion parity due to the right-hand neutrino Marana mass will not preserve any U1. So this is what I call Marana lepton genesis. In the scenario I have, is instead having the Marana mass gap, we will have some topological degree of freedom. And in fact, this topological degree of freedom can preserve instead of U1 B minus L, some discrete subgroup of Z2N of B minus L. It does contain fermion parity subgroup, let me write Z2N B minus L. And this anomaly structure will not be perturbative local, but non-perturbative global. And then non-perturbative global anomaly can be cancelled by TQFT or CFT, which is highly interacting theory. Which is not like mean field kind of quadratic term, but it's highly interacting. And I'll write some example of this theory. Yeah. Then my assumption to cancel this anomaly is due to the fact I'm emphasizing this B minus L is somehow preserved in the standard model and embed in the quantum gravity theory. And I want to assume such that B minus L will be eventually gauged, dynamical gauge. Then that anomaly need to be cancelled because dynamical gauge theory anomaly need to cancel. And just to clarify, when I say non-perturbative global anomaly, this global is not meaning to say this is global symmetry, but I'm saying this is in the sense of a non-perturbative global anomaly of Witten sense. The Witten-ness useful anomaly, like in the sense that you are doing a large diffeomorphism of gauge termination, such a particular function might change a phase in a discrete way, discrete phase, complex phase. Okay, so this might be a technical for some people, but I think you know what I mean. Right. Yeah, very good. That's good. Yeah. Great. Yeah, so then I'm going there for the discrete B plus minus L now, and I want to cancel them. And the main point is that without using right neutrino, we can add T or T, see if to cancel them. And let's go to which anomaly we're talking about. Perturbative level actually just this perturbative diamond graph. This is a triangle diagram involving crucially just the lepton number. The reason this anomaly is actually there is due to the fact there's some left-hand degree of freedom of lepton and right-hand degree of freedom of lepton. Without adding right-hand neutrino, you can compute this anomaly coefficient is basically something like this. When the anomaly is for the body QFT, basically you can write down a 5D invertible field theory that's exponential at some phase. You can also go one higher dimension, return a 6D anomaly polynomial, but right now I write 5D invertible field theory. This kind of concept is more like anomaly inflow from 4D theory to a 5D bulk of invertible phase. At the level you say about this phase as a classical, global symmetry, then this is not the pathology or sickness of theory, just because it's just something that you couple to a background field. So this phase is not the problem. The theory is still well defined, right? However, as I want to go is that I want to go to the direction that when the symmetry is not just global symmetry, but something you want to gauge it, then I want to cancel the element, especially in the way, not even in the perturbative sense, but non-perturbative global sense. Okay, so let me explain a little bit. So this ADA is actually just corresponding to this U1 cube anomaly diagram, and A is the U1 gauge field, and ARR is actually the U1 gravity, and R is the curvature two-form. So any questions so far? So yeah,
invertible TFT.
Yeah, invertible means this is a phase. Invertible in the sense this is exponential I some complex phase, and there's inverse because you can multiply this by the inverse of that, and all these are well defined as a classical way to capture some partition function. And this invertible phase has a modern concept, means some kind of symmetry protected topological theory. I don't know what I spelled this out, but this is a terminology for symmetry protected phases. Yeah, symmetry protected topological phase. Let me write it clearly. Sorry, symmetry protected topological phase (SPT), 或者是 topological insulated superconductor. Topological. the important for that is just that it's almost trivial as identity phase is 1, but it's not quite. It's just complex phase.
So this is Z5U1. So
Yes.
the left hand side is what is it?
U1Q?
No, Z5U1.
Oh, Z5U1 is, I mean, the 5-dimensional partition function. Yeah.
Okay.
Yeah, sorry for this. So when I write this full phase Z means the integer class. When I write this Z, means the partition function. Yeah. That is also notation. I didn't explain, but it's pretty common notation. Partition function Z and 5-dimension and U1 symmetry.
Okay, so this is something to do with U1 cube anomaly.
That's right. The first term is ADADA, so it's ADADA. So this anomaly is captured by this 5D term. And you can go to 6D anomaly polynomial, which will be F, wedge F, where F is DA over 2 pi. And R is the curvature 2 form. So ARR is the term to capture this A and curvature 2 form RR. And it's ADADA, AFF. And you can go to 6D if you write this DA as F, so FFF. So these are the anomaly inflow way of thinking. You can think about the anomalous series as an inflow to 5-dimension and invertible phase. And this is a concept of topological phase of matter. The reason we say topological phase also caused by anomaly, and this one-to-one correspondence is that topological phase has some boundary anomalous physics, such that boundary physics cannot exist by its own dimension. So right now I'm trying to rephrase the standard model anomaly in terms of 5D bulk. But we are just discussing, we don't want to have that just be a U1 phase, U1 global symmetry, but we're going to consider discrete again. So this anomaly also has relevancy for this genesis of a Marana gravitational topological lepton genesis. Yeah. I'm worried about this percentage of the charges, like running breakdown. So I might have a breakdown at some point. I need to change to computer, I guess. Let's see. Okay. So any question about this? I think this part is important. Either this is too basic or just if it's too basic, I can go quicker. Okay. Yeah. So then we kind of go a bit just speech like this is that structure actually you should remind yourselves that in the standard model is a lepton baryon current, the U1 of them. Actually, individually, it does suffer from some SU2 U1 instanton or sterile this kind of process. So what is preserves the U1B minus L in the standard model. So individual diagram of this type is not anomaly free, but the B minus L is. And what we draw earlier on the previous slide, we are showing this baryon pi is really 0, which I don't even say anyway, but the lepton pi is not. But because what is in the electroweak series, the only conserved series or conserved symmetry is really B minus L. So what it makes sense is if you consider the combined effect of this diagram. So what is left over is that the B minus L or B plus L is something you can consider. B minus L is something you are familiar with. If you compute the kernel of this B minus L, and if I normalize in a way such that the quantum number is quantized, which actually require to multiply by NC times, then the coefficient of that for B minus L is that this is basically has no anomaly involving the standard model gauge group structure, but it has this anomaly involving the F wedge term or DA term, or which I write term class C1, sorry, so C1 DA type term here. And R wedge R, which I write P1 from Juven class. Okay, so these are just this characteristic class notation. But the point is like this B minus L current is basically conserved in the standard model in the U1, but it is broken if you have the U1 cube anomaly and if you have an R wedge or gravitational background, right? And the coefficient of that will not be 0 when the number of family, NF is the number of family, and number of right-hand neutrino, NUR, is not equal. We know the family number is 3, but we don't know how many right-hand neutrino there are. So this is why the B minus L can be broken by the gravitational impact.
And on the other hand, B parcel does have mixed anomaly in the continuous global symmetry of B parcel with the standard model, which is the C1 through FOGF and C2 second chunk cost, also FOGF. But the coefficient of that is 2 times NcNf. So the conclusion of this line says that even though the U1 B minus L can be preserved, and it does have a gravitational anomaly, but the B parcel actually has a discrete subgroup which has the coefficient Z2 NF B plus L. Or if I write in the quantized way, Z2 NcNF Q plus NcL, this subgroup is preserved. And it does have also gravitational anomaly. Okay. So I don't know whether this explanation is okay. So I'm trying to explore the anomaly structure of the standard model. Say involving B minus L and B plus L symmetry, actually they does have a different conservation. One is U1, the other is Z2 NcNF. But when the gravities evolve, actually they can also be broken. Okay. All right. So so right now I kind of summarize the anomaly structure, and I'm going to go to detail. But I want to combine a different thing now about this topological degree of freedom, because I haven't even said much. And now if you just fall asleep, you can wake up again. So the topological degree of freedom, what are they? And where can you find? How do you study and why? This actually is the gap degree of freedom many-body system, and it's described by mass of homology category cobordism. And you can find in quantum Hall, fractional quantum Hall condensation system. But right now we are going to apply for beyond standard model BSM. And there's a technology used for quantum information computation. And then now I'm proposing it's part of a BSM dark matter structure. Okay. So let's just focus on this 4. And you have seen possible some latest model in condensed matter when you have a fermion hopping, you try to diagonalize. What happens is the spectrum can be gapless or gapped. And when we say topological theory, actually we require at least for those gaps, those sectors we have topological order usually have an energy gap. So this is energy spectrum gap when you diagonalize Hamiltonian. And the low energy of this theory at here can be T cap T. And when I draw this multiplicity of splitting, it means there's a multiple degenerate ground states. And this degenerate ground state actually has some dependency on the structure of the space manifold. For example, if you take something called the leveling filling fractional quantum Hall state of filling fraction 1/3, then on a torus in the space, which means you consider the like a substrate with some periodic boundary condition, then you can count the ground state on this system as a 3-fold ground state. So this 3 ground state has something to do with filling fraction. But one over n filling fraction has n ground state. So there's some topological dependency for this topological phase called topological order. And that's actually the structure I'm going to construct for you. And I want to say that new structure can use to cancel the anomaly for the standard model, involving this B plus minus L symmetry. Okay, let's forget about other part, just focus on this. And I also want to say, certainly in the standard model, we do have a gapless photon. So there's the additional gapless structure, but it does not affect me that I can still introduce a new structure involving this gap T cap T with gap topological order. And this type of material, so this type of kind of structure of the new quantum field theory I'm constructing is not far away from what already been studied in condensed matter, except the dimensions 1 lower. So when you see some of the talks about this applied magnetic field, measure the whole conductance, this is exactly what happened in what I propose as a new sector. They have a similar type of ingredient or the materials. Okay, let me skip a few things. The study for this anions or this topological phase has long since Feynman will check. But the main point is that the interaction is encoded in a way of how the particles are braiding or the excitation are braiding around each other such that their trajectory are linked. Okay, so, and the quantum field theory that described that will evolving degree of freedom written as also gauge theory, gauge field, evolving perhaps higher form. In 3-dimension situation can be a 1-form gauge field A and a dual 1-form gauge field B. So but in higher dimension as 3+1. So here this is 3D space F3 sphere. This will be 3D 3D series. So this is one form A is one form BDS, so-called BF series. So these are the type of fields you want to encounter. In 4 dimension, then the B can be 2 form, A is 1 form, and there's some coupling between the gauge. Oh, okay, that's the thing. I think my iPad running out of power, so let's switch. Sorry for this. Let's switch to my iPad, my laptop. Sorry, it's in the power boundary side. I have this.
Maybe you can use this charger.
Oh, but the problem is that the reason it's draining is because when I'm connecting to this, it cannot be, it cannot, it cannot, let me this first. You can help me to charge. There's a second pin. Uh, 30-second break. Back. Already? Oh, that's great. But really, it's one word. So, how do I do it? In the meantime, I think I can still go back to the slide. I have the laptop.
Sounds like electricity.
Huh?
I'm not sure if this is electricity.
Yeah, so the follow-up is that I was going to write down TQFT, which I haven't. And I'm going to write down how the writing neutrino is not a necessary thing to be added to cancel that anomaly. So this can charge, but can this be oh, can
It's not.
But you could see the screen of your notebook at some. In the beginning, you could see the screen of your notebook and then stop.
And share.
I use this implement to do.
You switch this.
what do you think? I'm using this for sure. Unless there's one more. But if we have one more, we can just use this. Excellent.
Or maybe you should use the. Oh. No, we see.
What is the voice one? What voice is fun? Do you turn on the volume? See? Yeah, it's here. Okay. Yeah, that's good. Yeah, that's all good. Yeah. So I can keep going. Right. Okay, thanks for the wait. Yeah, so I was explaining this topological theory. So this is more like actually the first one is a schematic way to write a Z gauge theory in 3D space-time with a B and A dual gauge field. They have a level n, the coefficients n, and they could have a mutual terms between a different set of gauge fields. So this thing is just a way to introduce more interaction. I'm trying to say this can be a theory of dark matter, and they are evolved to couple to B minus cell gauge field to a standard model, and this actually have a cell interaction. So I'm just giving you a kind of ideas then what TKT will look like. And I didn't construct this particular one for the purpose of standard model, but this is more like a set of TKT that are actually relevant in the sense of Darboux-Witten gauge theory or the discrete gauge theory. So this is a kind of field theory we are going to look for. But the particular one to cancel the non-view standard model is similar but still different. And I want to give you a sense how the field theorem writing will be selected like this, but more complicated than that. Because all this anomaly actually does not have a additional discrete symmetry anomaly that we need to cancel the anomaly standard model. Okay. So any question? So now I guess everything is in the context, and then we control a little even more detail. So we do consider the full standard model, and with the contents of everything you have done in the textbook. And I'm just yeah, it's fine. It doesn't work again. Okay, let's see. Okay, yeah. So this will be the quarks leptons written as previously I showed the chessboard, but right now I just draw everything in terms of biofermion. Importantly, they are 15 plus 1 missing 16 at most. And this number has this representation in terms of SU3, SU2, and subscript U1 of the hypercharge, right? And these are all the biofermion left-handed spin 1/2 of the space-time symmetrical of the spin group. To this button. So yeah, so they are spin the double coupler SO 3,1, and then this all are discover PX top quark, etc. Engage boson, we don't know this. So we are putting this context and ask again the question mark the right neutrino, which evolving, solving C-cell lepton genesis and neutralization. We are questioning this paradigm. Maybe we mean something. Okay, so yeah, and now I say that because earlier we identify the one high dimensional inverted phase capture anomaly standard model. I want to use that as an analogy that a single biofermion that we capture anomaly earlier. Okay. Yeah. So yeah, so this is actually a analogy between quantum condensed matter and the particle physics. Is that once you find some biofermion, you can relate this view as a degree of freedom living on boundary some one high dimension, let's say 4 + 20 topological superconductor. In particular, earlier we are showing the U1 case, U1 symmetry for B minus cell. If we consider the case of U1, certainly we can consider a case with single biofermion and with a mass, possibly single biofermion can have a Morana mass pair by itself or Dirac mass pair between the two. And this is a diagram, cartoon diagram to show the boundary state. And this is an energy spectrum is gapped. I even show this kind of a Brinon zone kind of band structure, right? It's a mixing between the space, picture of the topological phase and the energy band structure. This is a condensed matter presentation. But what's important is that when the B minus symmetry is discrete, say a discrete subversivo, which I'll give a reason. But if you take that discrete subgroup, actually there's a different classification of the topological phase. Instead of a Z integer class, it becomes a Z mass 16 class. So they are mass 16 class topological superconductor with a boundary type of not just possible only fermions, it's also about possible boundary state like this, but there's a new type, which is a topological order with a low energy DKFT or CFT. These are more interacting. The punchline is that there's an interacting theory cancel the standard anomaly involving the particle physics of biofermion. And this boundary state is what we want. And it connects to many past maybe 10 years, each decades of development of topological phase since maybe Leflin, Wheaton, Xiaogang with topological order, Wheaton TQFT, and people at Harvard thinking about topological phase transition and TQFT duality like Cyber. The reason is that actually this type of phase on left-hand side is particle physics. And this is not particle, but more like a vortex. So this is more like particle theory transition to a different phase to particle vortex duality. This is really schematic, but I try to say that this is really the physics. It's about one side of theory is particle-like, the other is different degree of freedom. And it must have evolving some gap closing, energy gap closing to reopen up. It cannot be smoothly connected. So any question? So the green part is the old one, and the new part is what we try to introduce. Okay. So if I use a summary of this anomaly cancellation scenario, say if I want to cancel the anomaly index to be 0 as a way to be consistent for the gauge theory, right? Then usually people use the green scenario of 18 particle degree of freedom, fermions, gapless gap, and or symmetry breaking phase or other phase gapless. I don't have time to read all this, but the main point is that we are using DKFT and CFT to cancel. These are new. Okay. So let me also present in a more formal way is that suppose I try to capture the theory in terms of path integral formulations, then I write a single biofermion and write on the Lagrangian theory. The statement is that under the U1 gauge and gravitational deformations and transformations, there is a partition function of the phase. We just write down the Z5 U1 you are asking. That phase is capture that, and that will be canceled by adding exactly invertible phase in higher dimension. However, when we break down this U1 down to some discrete subgroup such as Z4, then you can add in different degree of freedom and such that you can keep the bulk that preserve a different subgroup of symmetry. Okay, so then in some sense that what we are going to construct is the standard model under that large transformation of gauge gravitational deformation is not invariant, but adding this new degree of freedom alternative to adding biofermion physics actually can still make it invariant. Okay, so I think I basically summarized the logical flow there, the construction. Okay, so now I'm going to go to in which case this will become, I'm finished the first part. I'm going to connect to the non-particle work only. And this actually give me a pause to thanks some of the collaborators on this here, including senior people and the junior people in the past. Although the program I'm trying to pursue is actually most by my curiosity driven, but a lot of people I work with actually help in the subset of the projects. So that's why we have this acknowledgement. And yeah, so this is again a cartoon picture try to illustrate that if we write down the 3 generation of a standard model of biofermions, then what's missing is this 3 question mark, and the anomaly index we will emphasize in one case will be -3 plus number of right-hand neutrino. So the number actually, if you count the biofermion as 45, but or biofermion, it's 3 times 15, and missing possible some right-hand neutrino. And one of the indices I was explaining or mentioned earlier is mass 16, which means when this number is exactly 0 mass 16, it can be 16, 32, 48, then this anomaly is cancelled. But if it's like missing 3 right-hand neutrinos, 45 mass 16, which is -3 mass 16, then it's not cancelled. Then we can try to cancel this -3 phase. So we do input everything, discover and confirm in experiment the standard model. And we try to use the full path integral of the standard model, including all the familiar electroweak Higgs mechanism and Young-Mills and all the biofermion coupled gauge field, and write down this, and then do a large gauge transformation. Okay. I think before I put on TQFT, I give a picture first again, just summarize. Say the known physics in this cartoon involving the index minus 3 mod 16, but under large gauge formation is not invariant. I want to add a new TQFT CFT to cancel that. So this TQFT will transform in the opposite way to cancel that phase. And the physical interpretation is that now you can have the B and L related anomaly being canceled even mixed with gravity. Then you can gauge this B and L, and then this gauge B and L symmetry become a gauge force and interact between the known QFT theory and the hidden TQFT CFT we have not found. Okay, so that's the logic. So I'm drawing the cartoon picture to draw the new physics here will be evolving more like lines and surfaces as an operators, and they will interact with this particle physics. So this is a particle, and this is not quite particle, and the mathematics is cohomological Wilson category. Okay, then I think this picture probably is illustrative. Any questions so far? So you should think actually all the cross leptons in our body can connect to the Wilson line of B minus plus L to the hidden sector. So in some sense, the cross lepton is not quite isolated. In other than Yang-Mills force, actually they connect to the hidden sector. So in some sense, we may be some kind of a boundary state wire to the dark matter. And what's the wire? The wire is just the gauge field line of the B plus minus L. So we are kind of like more like a boundary state. Okay, and then this is a big picture of how this things can like cartoonish work together. Okay, so let me just say a few words about the indices, right? So the indices I would say is a 0 mod 16 if the preserved symmetry is a Z4 of B minus L, and then we have a 3 generation, and we add some right-hand neutrino number. As long as these are not totally numbers 3, then actually we can allow to add some new 4D hidden sector and 5D extra dimensional bulk, such that those indices can add up together to be 0 mod 16. And earlier we are trying to advertise one type of anomaly index involving U1, but when this U1 symmetry based on Z4, the precise way this index is captured by something called Atiyah-Parodi single eta invariant. So what happened is that this will be operators evolving. This will be the invariant evolving Dirac operator. So, and this Dirac operator will be the case that the Dirac operator is coupled to discrete gauge field, and in fact it's a Z4 gauge field. And E dot share with the spin structure with a fermion parity. So this is known as a spin group, as a double cover SO group, and with Z4 symmetry shared by fermion parity. Okay, and then one can compute something very mathematical cobordism is a classification of a structural manifold, and turns out this will be 16 class. So this is basically the machinery to compute an anomaly classification, and we can control the invariant. And once we have invariant, we try to make a gauge invariant full partition function, where the standard model carries some index -3, and you have other sectors add up to be 3 mod 16, then you will be fully canceled. Okay, so this is the logic. I don't know whether this is all clear. I kind of repeat a few times, but gradually I want to give you how this looks like. So then the prediction is that this will be all exist layer and then connect, like interact with us, but only through discrete gauge interaction. Okay, so I was showing you this anomaly, this U1 symmetry and gravity. But now let me just say again, or say more, is that where is the discrete B plus minus L symmetry come from? Now, I already mentioned earlier, the U1 B minus L is preserved, but there's a discrete Z2 NF B plus L. So we can actually analyze the anomaly for this both. This is a symmetry for the standard model. For the standard model NF equals 3 family, this will be Z6. So there's a U1 B minus L and Z6 B plus L symmetry. They do are anomaly free under the gauge force standard model, but they are not anomaly free under gravity because the lepton number mixed anomaly with gravity. When this index -3 family plus the right-hand number is now 0. So if that B plus minus L is preserved and consistent in the gauge quantum gravity theory, there could be dynamical gauge. Otherwise, it will be broken. But if we are consider they are preserved and they are not broken, then they should be gauged. Then without NF copy of right neutrino we are not found, then we add this TQFT. Let me just go further. This feels like I think we can skip. So these are just perturbative anomaly. And let me see, I think. So let me skip, because I think earlier I basically mentioned all this. So, okay, sorry. Let me just quickly I'll just say a few words. Like here, actually, I already mentioned that we do have distinction between particularly local Z class and non-particularly global ZM class anomaly. And we try to say this is different between small or large gauge information, right? And we do say that the gravitational anomaly or gauge gravitational are different due to the fact of how they couple to the field, right? The gauge field, gravitational field. And we do also distinguish between when this anomaly is background to whole anomaly or dynamical field, right? But now, the familiar calculation involving this there's a path integral type of this what you call path integral method. You can compute this transformation, whether it's invariant or not, up to possible background probe, and you can detect exactly the symmetry that is preserved. And let me skip this. I think we have mentioned that. And then in the standard model, we do have many diagram being checked, and we are only focused on this B and L and gravity, right? And the symmetry transformation of B and L under the Fox and lepton, some transform under this way, it will give a phase. And they are captured by more careful calculation indices, but I already give a formula, so let's just assume we know the result. But if you want to ask a question, you can interrupt me. And I also mentioned that because the phase in front of the B plus L transformation give a factor of 2 NF, so the discrete support 2 pi over 2 NF is preserved, and we are looking into that. Let me skip this part. These are not so important, and this part is important. So when the B plus or minus L symmetry is discrete, this table shows the classification indices. It requires some more technical calculation, but the outcome is shown in the table, which we computed. When we only consider U1 class, the anomaly indices, which is captured by something called topological phase of cobordism, TP5, is just a notation. The main point is that that classification is integer Z class. But when the symmetry is discrete of B plus minus L, the classification actually is Z32, Z2, Z9, etc. And the main point is that given the standard model content, you can check whether this anomaly indices under this classification is 0, modulo this ZN class. And if it's not, that means the standard model is not part of anomaly 3. And if you want to cancel that anomaly, then you have a room to aid BSM sector. So we can also compute a single right-hand neutrino indices and versus the standard model indices. And we can check that without right-hand neutrino, the standard model does have anomaly. Okay. But now the game is that we want to add new degree of freedom without right-hand neutrino to cancel this modular 16, modular 9, or modular 32 type of anomaly. But here I'm giving you the symmetry as a Z4, ZA, etc. And we can ask where are this symmetry coming from? Is that the whole symmetry? We're just taking some subgroup B plus L, B minus L. For B minus L, there's a good reason is that if you consider BSM deformation, it's pretty natural to consider full fermion deformations. In the sense that this is the next higher order interaction. Or also in some senses, it's a way to go beyond the mean field. And if all the quarks and lepton, let's say, are coupled in some way, and such that to preserve some symmetry, and the natural symmetry you can preserve is actually the Z4. The reason is that this X symmetry right here is actually a combination of B minus L and hypercharge. When you define this quantum number, as Weyl and Z did in 79, you will find out the quark and lepton sit nicely as charge 1, see over here. So it means that actually they can sit in the same multiplate under the Z4. And it turns out the Z4 is actually the center of the spin 10. Also for people study spin 10 gradient by theory. Although this is not a necessary condition, but this Z4 has a multiple benefits. It makes all the fermion charge under 1, under the Z4. It also sits nicely as the center of the spin 10. So which means the Z, center Z of the spin 10 is Z4. Yeah. Write it down. Yeah. Means the center of the V on the legal spin 10 Z4. And that means that Z4 X in the same way as the 16-dimensional multiple of spin 10. So, and together with the reason, say, you are allowed to aid some symmetry preserving deformation, the full fermion is the simplest one. And for people who study like interaction between fermions, like such the EIK it's also very common for people nowadays thinking about quantum gravity theory from quantum mechanical system. Then full fermion deformation is very natural, and from the BSM deformation is essentially natural to consider that. So by this deformation, it's easy to break down the U1 of continuous B minus L down to a discrete, and it can break down preserve some discrete Z4 of B minus L symmetry. And that's exactly the X symmetry I say here, the Z4X. So any question for this? So there could be a structure of a discrete B minus L symmetry preserved as a Z4. Certainly you can add higher order A fermion interaction, but this is even much more irrelevant term from the perturbative algebra point of view, but it can preserve a larger Z8, etc. symmetry. So if I consider Z4, then it gives you a reason to consider the classification anomaly involving Z4 symmetry, and that's why it gives the Mach 16. And this Mach 16 pretty much closely connect to the number of Weyl fermion in the standard model, which is 15, nearly 16, right? And then from the other side, the B parcel was already Z6 B parcel. I computed this earlier, right? And it's basically Z8, Z6 B parcel, Z18, if you quantize properly. And I want to mention a fact, which might be technical, but it turns out that the number of NC is 3 and NF is 3 comes naturally from a topological point of view. Instead of consider something like a horizontal symmetry of 3 flavor and rotate between different families, and that's usually colored. Some people might consider that. This is all from the legal perspective people had in the past. I don't need that. But there's a nice scenario, turns out, this is technical, but it turns out, I just summarize anyway. So if you have 3 families of the standard model, and if you consider a color number extension in the sense of group extension into a Z9, then the anomaly structure of the 3 family involving the space-time spin group, which is gravitational probe, and Z6 B parcel symmetry. And this notation means they share fermion parity. This subscript means this and this. They need to model the common Z2F. This extension by Z3 color to this one actually be a very consistent construction for cancel the anomaly of the standard model with missing 3 right-hand neutrino by adding the topological order. Okay. So this is a group extension, some kind of construction required. And I think for the general high energy community, I don't think this is a known statement, but the main point is like this structure actually coincide very tightly with a topological field series structure, and I'm going to explain. But I'm trying to summarize the data again, but now I give you, let me see. Go down. Yeah, now I give you the data, the standard model with NF family, maybe 3 family, the indices of them, which actually shows mostly non-zero for simple symmetry we consider for B plus and B minus L. So we want to cancel these anomaly indices, right? And I try to write down here a 5-dimensional bulk term from the continuous U1, which we already write. A, DA, C1 is DA. A, DA, DA, C1 is a trend class. A, DA, DA, and A, P1, A trace are which are term. And when you go to a Z4 subgroup U1, there's a 5D invertible phase become a Mach 16 eta invariant, which is basic classification of topological superconductor of 16 class. Okay, so here's the TQFT is under this transformation, this is not invariant, and the phase will be root Mach 16 phase. I want to control a TQFT for that. And let me skip this whole part. And let me make sure how much time do I have? We have 10 minutes. Yeah. So I'm getting the construction of that. Let's see. Okay. Yeah. So yeah, let me skip this part. I think the slides will be available. So actually, let me just all skip this part and then go to the TQFT because the construction may be easier once I say what exactly TQFT look like. Okay. Let me show you the final theory first, and then we can go through the discussion. So we have write down the standard model pattern equal earlier, right? And I claim that there's a phase non-invariant under the Z4 gauge of B minus L or other B parcel symmetry formation and gravitational deformation. And Now the indices, in order to sum to 0, I claim that one construction can be TQFT. So this will be a formal way to present the TQFT. Okay. This will be not familiar to most people, but let me try to explain. Okay. So this will be involving curly A as a Z4 gauge field B plus L, B minus L, sorry, the Z4 gauge field. And this curly A is also coupled to the quarks and lepton here through the covariant derivative. Other than the U1, SU2, SU3 Yang there's also the gauge field, Z4 gauge field coupled to quark lepton. As I say, all the quark and lepton has charge 1 under the Z4. That's why there's such coupling. So this Z4 both coupled to the quark and lepton in the standard model and coupled to the TQFT of this theory. And how do we see this as TQFT? First of all, involving some differential form like, but precisely it's actually a cochain field. Cochain field is a way to put a manifold not in a continuous way, but in a triangulated way, which means you triangulate the continuous manifold, and then you put down simplicial complex on a manifold, and then assign some cochain field class on the simplicial complex. So B here is a two-form field in the continuum, but it will be a two-dimensional cochain field. A here is a one-dimensional cochain. At this moment, you might be worried, saying, why do I write cochain field and why do I triangular manifold? Because you say maybe we are considered quantum fields to be continuous. But mathematicians tell us actually continuous manifold is always triangulable. So this actually is a pretty much precise way that you can convert a continuous manifold, the discrete gauge field, as a differential form into a cochain field. There's a better reason to write cochain fields because it's actually more mathematically well-defined and the pattern can be rigorously computed. Once you do know how to write it as a cochain field, you can convert to differential form. So I just will give you assurance. Actually, you can write it as a differential form if you want, but mathematically it's better to write as cochain field. So BDA is actually what I showed you in multiple slides earlier about this BF theory, right? And this curly A cube is actually the coupling between the Z4 gauge field, the new gauge field from the TQFT side with the B minus L Z4 gauge field. So there's a coupling of like there's a quasi term of little a coupled with A cube term. While the ABK, I don't know what the mathematician people study this, from cavalry invariant. It's a invariant of Mach A class captures something called Kitov-Marana fermion chain. This actually is something people try to construct as 1+1D topological superconductor wire of some pairing for p-way pairing, and the classification that turned out to be 8. This 8 class turned out to be useful and important here is because it has something to do with the Mach 16 anomaly we are trying to cancel in the standard model, the Z16 anomaly. So there's a coupling of BDA, just like the BF theory I showed you earlier, and there's a coupling between the B minus gauge field with the dynamical little a. So little a little b is dynamical, and the big one A is B minus L, can be viewed as a big one B minus L field, but at the higher energy scale, like near the quantum gravity, it might be gauged. That's why we consider anomaly cancellation involving that. Yeah, and then the other part is actually coupling also in a 3+1D wall and the 4+1D wall. So this part is a 3+1D theory, and this one is 4+1D 5D theory. So all these terms, my claim is that this term can be appended to the standard model such that the Mach 16 anomaly is cancelled. And this certainly is technical. For people who are not familiar with this Kitov chain, probably will be not easy. But I want to give you a sense like this is maybe seemingly very exotic and familiar theory, but it captures the same anomaly as a single right-hand neutrino. So by removing the right-hand neutrino, I can actually add instead this sector as a hidden sector. Any question? Okay, so yeah. So let's say a few words. Yeah,
I have to run now.
you don't know. Okay.
Thanks.
Oh, thank you.
Thanks for coming.
Thank you. Oh, sorry for that.
Enjoy.
Yeah, sorry for not being able to finish before that, but thank you. Yeah, so so that's the TQFT. But let me put a few words like what's the structure behind, maybe help you a little bit is that
The invariant actually earlier write the Mach 16 invariant involving this Z4 gauge field, and here I write curly A. Somehow I need to take a Z2 discrete subgroup. It's a detail. It's because the Z4 Mach fermion parity Z2 is a Z2, but this is a Z4 Mach Z2 subgroup. And it has R Brown cavalry Marana chain invariant. And then only when we take a discrete even class subgroup that actually you have a expression that decompose this even class of Z16, which is running from 2, 4, 6 in Z16 in a ZA subclass, such that it can decompose in several layers, which is binary by 0, 1, 0, 2, and 0, 4. This combination turns out have a construction for cancel the anomaly by TQFT. That's why we are considered this Mach A subgroup. And so yeah. Yeah, if you have a question, you can ask. So this is basically required to control the TQFT, basically analyze the invariant and try to understand the mass structure. Okay. So yeah. Yeah. And let me show you maybe a slide for. Okay. Yeah. Okay, so, and let me comment about this construction. How does it help, for example, to look at the tree family? Okay, so this part, because I'm not in iPad, so I couldn't write directly, but let me try to help a bit. Let me just go to a punchline that only when the family number is multiple 3, this index of anomaly is Mach 9 class, and the anomaly index actually is 3 Mach 9 for each family. When you have a 3 family, sorry, I think I said it wrong. When you have a 3 family, the anomaly index is 3 Mach 9. But it turns out that if you want to construct the TQFT theory to cancel that anomaly, it turns out it requires a particular extension from the known Z3, Z6 subgroup. The Z6 is Z2 times Z3 because 6 is 2 times 3 and 2 and 3 and co-prime. So you can take a Z3 subgroup of that. And the extension involving Z3 extend to Z9 actually can be exactly matched with this topological TQFT construction. So this is actually what called symmetry extension construction. It's not very simple to explain, but let me try to go through now just a little bit. So you have a sense like I'm not just saying something mathematical, but essentially it's actually very also physical. In which sense? In a previous scenario in a standard model, actually what happened is Anderson-Higgs mechanism. So there's some kind of symmetry breaking, like SU2 weak and U1 hypercharged break down to U1 EF, right? But there's an extension construction we are going to use. Is that we don't really break down like a global or this gauge group down to a subgroup like Higgs mechanism, but we kind of extend that. By extension, it means more like vibrations or some kind of group extension, such that you double cover or ends cover the original group and try to analyze the original anomaly structure of the original group, and then try to make the anomaly become 0 or so-called cancel or trivialized by the extension. So this construction 3 is very different, both by physical and mathematical sense. In the sense that you are not trying to add Higgs field and break down a gauge group, but you are trying to add degree of freedom and then enlarge the gauge structure. So this is a third construction actually we require. There's also other things not directly used in my talk, but symmetry mass generation involving symmetry preserving and highly intelligent mass gap, but let's not go in there. But I want to contrast 1 and 3 and then give you a sense the difference. So TQFT construction we are using actually symmetry extension. So in Higgs mechanism, you know the BCS Baryon-Kubo reversal will cannot break down U1 gauge put on Z2. But in the case of a standard model, the U1 is similar to the case of a SU2 times U1, and unbroken subgroup is U1 EM under the Higgs. And what happens in BCS is there's a Cooper pairing and BDG equation solving of this equation break down U1 onto Z2. And no image of this theory of Z2 subgroup can be gauged as a Z2 TQFT or Z2 gauge theory. Some people call it topological order. In some sense,
you also happening phase of matter with global symmetry broken, let's say like Holden spin chain, this SO3 symmetry protects in the spin one symmetry this state. And on the boundary, SO3 can be broken down to subgroup or nothing. Same thing for time reversal. It can be broken. So this will be a symmetry breaking way to construct a boundary state or even a so-called just a gap state on the boundary, right? So this is breaking. But what I'm going to show, and I already show a few times, is actually this group extension. Instead of breaking down the G down to a subgroup, you basically extend such that this group K is a normal group, and G is a quotient, and G hat is a total. This is more like a vibrations or extension construction. So what happens is that we can pull the Z4 and the B-SL symmetry and B-SL symmetry here, and with some space-time symmetry spin structure, and also the S2, S2, standard model structure here. Instead of using Higgs to break down to a subgroup, we'll add a new gauge field degree freedom and try to fiber or extend group extension over it and to a G hat. And what happens is that then this K gauge structure, gauge field, become a new degree freedom that involving anyons or fractional excitation. So that's what the mechanism is really come about. The mathematics for that is actually a bit complicated, involving spectral sequence. I think to really show the trivialization of the anomalies involving something called Atiyah Hertzsprung or Leibniz Herschel Serra spectral sequence computations to show the criteria to trivialize the anomaly, but I didn't really explain this math. So all you need to do is know is that actually this extension is not just writing down a group extension only, but there's a criteria need to be satisfied. When the theory has a G symmetry anomaly, you need to do extension to show the trivialization of this anomaly. And there are some detailed construction, but we can actually give a talk on this. So maybe you can have a look on this when you have a little time to enjoy his exploration as an example of Z2 symmetry protected state with possible gapless edge. Under a Z2 symmetry extension to a Z4, there could be a Z4 symmetry extended boundary state and it's a gap phase. So in analogy to my system, instead of consider Z2 to Z4 extension in 2+1D system, we consider a 4+1D system where the 3+1D boundary standard model with the structure of this group of this extension replaced to what I show in the slides, which I already showed earlier in the later part slides like this. You put a standard model group as U to U1 and Z4B plus B-SL here, spin of the span-time symmetry, extend by some larger group, by some finite group. And this extension group is actually basically will be the new gauge structure of the TQFT. And this Z2 or Z4 or layer of the Z2 is exactly related to the gauge structure for the TQFT. And this theory will be appended to the boundary together with standard model and make the closing gauge invariant. Okay. So pretty much that's it. Any question for now?
Well, it's already time.
Okay, so I guess we've had about time.
Can you wrap up?
Yeah, we can wrap up. Yeah, what time is it? Oh, it's already over time. Yeah. So I guess I will skip the other discussion, except that finally I want to say that once the hidden sector is TQFT, then you can revisit the previous scenario people consider so-called Marana lepton genesis, which has right-hand neutrino, or gravitational lepton genesis, which has no right-hand neutrino by using gravitational instanton or gravitational wave to generate lepton number through this diagram, which I showed earlier. Just this one. But now we have a TQFT, so the scenario can be a topological field theory, maybe the source of the decay to the particle. So there's an unparticle, non-particle TQFT or anion degree freedom through the discrete gauge B plus minus L gauge interaction decay to the lepton number in the standard model. Yeah, that's it. And there's also a revisit of a possible beyond seesaw mechanism scenario. I will just leave this here and then show there are many comparison or scenario with the table and I leave the slides on my webpage and you can have a look. And let me just say conclude that possibly if you question stereo right-hand neutrino may not be there, then using topological degree of freedom with low energy TQFT and known as topological order this type of phase might be a candidate dark matter. It might explain how the lepton neutrino get little mass through interaction with this TQFT. It may explain the neutrino oscillation through the interference with TQFT sectors. It may also explain the origin of leptogenesis without using right neutrino, but decay from topological order with some kind of anion degree of freedom. Yeah, so I'll leave it here and thank you for your attention. Yeah. That's all, Jeffrey. Thank you for staying.
Thank you very much.
Any question? Yeah. And right now, I want to ask you again, how much do you think this might be a possibility? After listening to this talk, do you find this scenario might sound a possibility to you?
Usually things seem possible before you analyze them in detail.
Mm-hmm.
So many great ideas seem possible before you analyze them in detail. That's I think.
Okay. Digest.
You have to
before
digest
you-
things. Thank you very much.
Thank you.
Thank you.
Thank you.
Ah, sorry.